apologize. Good morning, everyone. Technical issue, but we're going ahead and getting started there. Welcome to NCASA's Data Science webinar series. Thank you for attending today. I am Elizabeth Manshart, past president of the North Carolina chapter of the American Statistical Association. NCASA and our industry interest group are excited to bring you this webinar today as part of our commitment to provide professional development opportunities to the community. We will have 2 more webinars this calendar year. Both are machine learning webinars later in the fall. We will have part 2 of Introduction to Machine Learning presented by Funda Gunes from SAS. That will be Friday, September 27th at noon. And I believe registration is live for that event. And then we will have Interpretability versus Explainability in Machine Learning by Cynthia Rudin from Duke University on Friday, November 1st at noon as well. Registration will open later this month, so please keep an eye out for registration. North Carolina chapter of NCASA is one of the largest ASA chapters, and we have a very active community with a lot of events. So if you're not familiar with our organization, please take a minute to take a look at our newsletter, our website, or our social media accounts to find another event that might be of interest to you. Links to NCASA homepage and webinar series are posted in the chat box for those who are attending. And this video will be posted on our YouTube channel if you'd like to revisit it or pass it along to a friend who may not have been able to attend today. So again, thank you for attending NCASA webinar. If you have any questions during the webinar, please type them in the group chat, and Eric will read through those during the questions period at the end. With that, we would like to welcome and thank Aric LaBarr. Aric is an associate professor of analytics at the Institute for Advanced Analytics at NCSU. Aric helps innovate the current structure of education to better prepare a modern workforce ready to communicate and handle a data-driven future. He develops and teaches courses in statistics, mathematics, finance, risk management, and operations research. His focus is to teach, mentor, and serve students as well as businesses on modern analytic techniques for making data-driven decisions. Aric also did a webinar for us early this year, and that is available on NCASA YouTube channel, which is on the webinar website posted in the chat box. So thank you again, Aric, and please take it away.
Thank you very much, Elizabeth. It's a pleasure to be here again. It was a lot of fun being able to do the last webinar, talking a little bit about sort of how to bring together executives as well as data scientists. This webinar is probably a little bit more focused on the data science side of things as compared to the other one, but still very interesting. I think it was actually more posed by a person really on the executive side of things when someone asked me a question, you know, is data science really a science? And that really got me thinking. I'm like, you know, that's a very interesting question in the way of what we normally think of as science. And, you know, is data science really one of those? And so really that was the foundation for a lot of what this presentation is how can we make data science a science? And I think one of the main keys to that is proper model validation. The notion that if we're going to make sure that we are sharing our results and then sharing also the decisions that we think people should make with our results, that we have a way of being able to communicate that what we've done is actually meaningful and what we've done is checked so that we can replicate our results in a way that people can trust them. So along those lines, you know, it goes back to the idea of the simple question that we all ask ourselves, or at least I'm hoping we all ask ourselves whenever we do analysis. And that really is, how good are our results, or how good are your results? If you don't ask yourself this, I hope someone you know asks this of you, because it's always good to be able to make sure that people keep us in line and keep us in check. And so how do we really answer that question? A lot of it deals with the idea of prediction and evaluation. It's extremely important to make sure that we evaluate our predictions from a model, or evaluate our models in totality, to know how good our models actually are. And there's a difference to me between the idea of accuracy as well as validation. If you have a very accurate model, to me that means that you can predict the data that the model's already seen very, very well. We typically call that training data, where we basically say, all right, you've done a good job at predicting things you've already seen. And that's good. But outside of just accuracy, we also want models and techniques that have been well validated. We want to make sure that we meet validation concerns as well. The idea of predicting new data, the idea of expanding our model and generalizing it to data it hasn't seen before. And so these are always key things. And again, the reason a lot of this talk has come up recently and why it's so important is because of recent problems in actually the world of validation and really the world of statistics and mathematics, data science. It's, wow, been a few years now since this Economist article came out. And if you haven't gotten a chance to read the Economist article on how science goes wrong, I highly encourage it. It's a wonderful article. I've pulled out a couple of quotes here from the article. First one being, the simple idea underpins science. Trust, but verify. Results should always be subject to challenge from experiment. And I think we probably all would agree with that statement, that really the whole point of science is to be able to test things, to experiment on things. We should trust what science tells us, but we also need to verify what science is telling us. The second quote here is probably a little bit more controversial and, in my mind, almost a little bit more extreme. Modern scientists are doing too much trusting and not enough verifying, to the detriment of the whole of science and of humanity. Again, that's a rather weighty statement right there. Probably, trying to help people read the article a little further. But I do think it has some importance that without the balance of trusting and verification, of both trust and verify, we can be caught going down one path a little too much. One example of that, actually, or a few examples of that the article actually lists, I've sort of talked about a little bit here, and that's the crisis of false findings. So really, the downside of a lot of experiments that are out there, and really some of the publication biases that we know exist, are the replicability of things. Again, the ability to verify. So let me walk through a couple of examples. The British Medical Journal ran an experiment of their own. What they did is they basically wrote fake articles, wrote fake journal entries, and then sent them off to their referees. Now, these fake journal entries and these fake articles had major errors that were in them. They intentionally made articles that they were like, there's no way this is actually going to get passed. Unfortunately, 92% of their 1,500 referees missed some of these serious errors in these papers. Lancet, they accept 5% of papers, but they estimate themselves that half of those are actually worthless. Bayer Healthcare recently tried replicating 67 studies and were only able to do it 25% of the time. And again, another one, Stan Yun examined controlled experiments trying to replicate 12 data, we'll call them discoveries, things that clinical trials and things along those lines were supposed to tell us were true. 0 of them were replicated. 7 of them had neutral results, and 5 of them actually reversed the results of the original run. I had a friend tell me a story one time about he was trying to replicate results in his department, and they brought in someone who they were trying to replicate the results of. And they were from another school and another college. And they were like, all right, look, we've been trying so hard to replicate your results, and we just can't get it to work. What are we missing? And, it's part joke, but it's also part serious. The person who they brought in said, well, you don't worry. It didn't work for me the first 6 times either. And so it's one of those things we have to be very careful of in this field, right? We get rewarded a lot of times for finding results, but we don't necessarily seem to see the same reward for not finding results. So, I'm an economist by trade, so I believe in incentives. We're incentivizing people to find things sometimes that may not be true. And so again, I go back to that same question that someone asked me at one point: is data science a science? And I said, my response then, and I still believe it now, possibly. Let's talk about what science is. Science is the systematic study of the structure and behavior of the natural and physical world, or knowledge obtained about the world by observing and experimenting. Now, this comes from And then it got me asking the question, well, what is an experiment? Well, again, formally, an experiment is a test done in order to learn or to discover whether something works or is true. And again, I just think back to the field of statistics, and this is exactly statistics, right? I mean, that's the whole point, is we're trying to learn and discover something that's true. And we use data to be able to do that. And so really the whole point of, is data science a science? Yes, I think it can be. But again, I have to go back to that same notion we talked about previously. It is a science, but we have to be careful not to just trust results without verifying them. And so why is this, again, potentially a problem? And I don't know about you all, but XKCD gives me basically anything I need when it comes to making fun of a certain subject. And so, you know, I'm going to give you all a moment to sit here and appreciate this XKCD comic, and then I'll sort of summarize it. So the general gist of the comic is jelly beans cause acne. Quickly, scientists investigate. And so they found no link between jelly beans and acne, at least at a p-value of 0.05. And so someone says, well, that settles that. And then someone else goes, well, it's here, it's only certain color that causes it. So again, send the scientists back. And so they test a variety of different jelly beans: gray, tan, cyan, green, mauve, orange, peach, and so on and so forth. And they test 20 different colors. And they're using the same statistical test. And in 1 out of 20 tries, green jelly beans seem to cause acne. And again, the whole thing that you see at the end is green jelly beans linked to acne, 95% confidence, only 5% chance of coincidence. And again, it goes back to that same idea that we know in the world of statistics. If you keep torturing the data long enough, it'll tell you exactly what you want it to hear. With a statistical test that's only supposed to find errors, you know, or limit our errors to 5% of the time, and if we run that same test 20 times, well, 1 out of 20, 5%, we'd expect to be an error. But again, this is the problem sometimes with data analysis. The natural human brain wants to find patterns. And when I've given this talk before, I always like including these. I've never done this before on a webinar, so we'll see how it goes. So in trying to find patterns and trying to help people understand that the brain naturally wants to find patterns, I basically went to Google and I found different cloud pictures that are out there. And I just basically grabbed a bunch of cloud pictures that I thought were interesting to see if people saw things in the clouds. And so like I said, I've given this talk many different times. I usually ask the audience what they see when they look at these clouds. Obviously, I can't do that so much here. But here we can see, you know, this is an easy one. You know, this looks like a heart. You know, maybe you see other things, but, you know, I think the easy answer would be a heart. I like this one, though. I'll give you a moment. What do you see? Well, I have a couple people coming on the chat. That's a great way of doing this. If you want, throw in some answers on the chat if you're interested. I keep seeing horse. Now you start wondering about crowdsourcing, right? The idea that maybe everyone else sees horse and said horse, so now everyone sees a horse. You know, one of the most popular answers I also hear is a crab. You have the one claw, big claw on one side, a small claw on the other, and a bunch of different legs going down below. So I see crab. Let's see here. The world. Oh, that's an interesting one. I haven't heard that one before. So again, you know, we have a couple of these that may be, you know, a little bit more unique. So again, here's another one I actually found. That one, again, a little bit more easy. People see a cross in the sky when they look at that one. This one I love because I've gotten so many different answers on this one. Tell me what you see. So whale is a popular one. Elephant. Yep, I've heard people say elephant before. You see an elephant's trunk. Okay, good. Good. Yep, dragon. That's another popular one. For those who may not be able to see the dragon, imagine that cloud on the upper right-hand side is the dragon's head. You can even see the eyes, the mouth, and the nose, and it's breathing fire coming out the other side. It's one of those things where one of my colleagues, when I was showing him this picture, he was like, it may be a dragon. He saw something different. I'll tell you in a second. He's like, and I told him, I see a dragon. And he goes, well, if it's a dragon, it's a rather fat dragon. I'm like, well, fair enough, but it's still a dragon nonetheless. A camel, that's another popular one I've heard. There's one, a person with a hammer. Yeah, I've actually heard people call this Thor, where you actually have, if you look at the hump in the middle, you can almost imagine a knight with horns as a helmet, and you can see on the lower left-hand side he's holding a shield, and he's raising his arm with either a sword or a hammer, and he's bringing it down. So again, it's always interesting. But the thing is, let's be honest, these are clouds, right? I mean, that's all they are clouds. But the brain naturally wants to see patterns. It naturally wants to find things. Again, it's scary. I had another colleague of mine, and I'm going to date myself here as well as date my colleague. One of the things that's they were giving a presentation one time with transparencies. Like I said, I'm dating myself here on giving presentations with transparency. So he had his stack of transparencies that he brought into a presentation, and he's sitting there in front of a group of doctors. And he basically throws the transparency down and goes, as you can see from this chart here, this relationship, as this one variable increases, this other variable has a tendency of increasing. And all the doctors are like, oh, yes, yes, yes. Makes complete sense. Now, we understand that completely. Well, about halfway through the presentation, he realized the transparency was upside down. He had flipped it over on the wrong side. So he's like, oh, I am so sorry. And literally flipped over the transparency. And now the relationship was negative. And he, again, greatly apologized. And the best part, he said, the doctors in the room were like, oh, that's okay. That makes sense too. It's, and they started explaining it away on why the relationship would be negative. And again, it goes to the idea people want to find patterns in whatever they see. And this is why we have to protect ourselves, is we look so much sometimes to find something that, maybe we're seeing something because we're looking so hard for a tree in the forest. So let's talk really briefly about the idea of data splitting, and then we'll get into a technique that I think can actually help with all of this. So really quickly, one way of trying to validate our results that a lot of modelers, data scientists, analytics professionals, statisticians, whatever you want to call us, whatever we do, one of the common ways of doing that is training versus testing and splitting our data. Whether we split our data into 2 groups, into 3 groups, training, validation, and testing, with a variety of different percentages, 60-20-20, 40-40-20, 70-20-10. But the main goal is to set aside some piece of the data that your model has never seen, that your selection algorithms have never seen, with the goal of basically going, all right, at the very end, how good is my model? Really, how good is it? And the best way for me to do that is give it new data. And when I give it new data, then I can tell someone, okay, when you run this in a real life scenario, this is what you should see. That's the idea of training versus testing. And, there's a variety of different flavors. I'm not going to go through all of them by any stretch of the imagination. That's not what this talk is about. There's cross-validation. What if the one little group that you set aside just happened to be lucky? So why don't we take many little groups and build many different models and sort of average out the results? That's the idea of cross-validation. And so these things are great ways of doing it, but they don't always protect us and really answer the question of how likely were we to get the results that we had due to, again, sheer randomness. And so that's what I really want to focus today's webinar on, which you might be interested. We're already 20 minutes in and I haven't even started talking yet about target shuffling. The main thing I want to talk about today is the idea of target shuffling. Target shuffling is a technique that was recently sort of brought back to life. I don't want to say it was invented. I mean, it was, but it wasn't. It's also known as permutation testing. But now we have the computational power to do it a little bit easier than what we could have done mathematically a long time ago. But it was more recently brought back to prominence by a famous data scientist, Dr. John Elder. And Dr. John Elder used this originally to actually do this for hedge fund modeling, to try and explain to people how his hedge fund strategy was actually better than random. And so John and I are friends, and we've talked many times about this over the years, and it's something where I don't think it always gets the value that it should. So let me talk to you a little bit about target shuffling. So what is target shuffling? Well, I want you to imagine we have a very simple problem. I'm trying to predict whether or not you're going to default on a loan. Okay, so I have a column here called default. So with default, I'm going to sit there and say, okay, I'm going to try and predict this classification of 0 and 1. I'm going to use a couple variables to do that. I'm going to use what income you have and whether or not you're currently a student. Okay, so I'm just going to make a very simple model. So I'm going to take these two variables, I'm going to build a model on default, and then try and record some model metric that comes out the other side. You know, there's a variety of different ways of, you know, evaluating a classification model. So, you know, maybe we do something like an area under the ROC curve, maybe you do concordance percentage, maybe you do lift, something along those lines. But we're recording some kind of model metric. But now we want to really figure out, what's the probability that I just got lucky? What are the chances of me actually just getting lucky and my data just happened to be structured in a way that I found a pattern that's not really there? Well, one way to evaluate that is target shuffling. So I'm going to walk through the steps of target shuffling with you all today and sort of match it up with that same, you know, column set and table that I was working with before. So the first thing we want to do in target shuffling is randomly shuffle the values of the target variable while leaving the input variable values the same. So basically, don't touch the x's, just close your eyes, mix up the y's, and just shuffle them all around. Now, we would imagine what we're actually doing here is breaking the relationship between the x's and the y's. And that's exactly what we're trying to do. We're trying to remove any possible relationship between the target variable and the inputs. So again, for example, as you can see here, you only see 6 observations, but I have 3 1s and 3 0s in the default column. I still have 3 1s and 3 0s in my new column Y1. It's just with those 3 1s and 3 0s, they're just in a different order. And again, the whole goal here is if I were to randomly assign these 1s and 0s to people, same number of 1s and 0s, but just randomly shuffle the order of these 1s and 0s, if there was a relationship between income and default and between student and default, I've probably broken that relationship. Well, let's see. So with that new target variable, I'm going to repeat the model building process. Now, ideally, you're going to make this an automated model building process because I'm going to ask you to do the same thing thousands of times. So if I repeat the model building process, I basically want to select what variables are important, find the best model, and so on and so forth. So again, I'm going to take income and student. Instead of predicting the actual target variable default, I'm going to predict this new shuffled version instead. Once I build that model, again, I'm going to save the best model from that selection technique, and then also record that model's measure of validity. So again, however you want to compare models, however we compared models the first time. So we recorded this model metric in the beginning. I want you to calculate that same exact model metric every time you build a model. Okay, so again, maybe that model metric is area under the ROC curve, maybe that model metric is AIC, maybe that model metric is lift. Whatever you're doing, record that same model metric. And now I want you to do it thousands upon thousands upon thousands of times. So reshuffle the target variable again, build another model again, record the model metric again, reshuffle again, and so on and so forth, reshuffling this target variable over and over and over again. And then what we're essentially going to do is we're going to look at the distribution of all of these model metrics across all of these models and really see what a histogram of all of these would look like. Essentially, what we're actually doing is simulation. We're simulating many different instances of our data, where all we're doing is randomly shuffling the target variable. And then what I'm doing is I'm recording the results from each one of the models that I'm building, and then visualizing these results in a histogram. So again, all I'm doing is just a simulation. And so I see this simulated values of the area under the rock curve from the same data that I actually showed you in that table. And we see a lot of different values for area under the rock curve. Well, what we want to do, though, is we want to evaluate where our original model's validity measure falls on this distribution. So that's great. You have this distribution of values of all of these models that you've built, but where's yours? Where's the real model metric? Where's the real data in all of this? And the reason we're doing this is we're essentially trying to build something that protects us against the placebo effect. Essentially, what I'm trying to build with target shuffling is a control group. I want to be able to make sure that I can tell someone that I didn't just get lucky and the data that I had just naturally finds patterns. You know, I want to know that my model is truly different than the model of any random order of target variables. Again, going back to how John first did this when it came to his hedge fund strategy. What he basically did was said, here are the days I told you to trade. Here are the days I told you to sell. Here are the days I told you to buy. Now I'm going to randomly shuffle those. And I'm going to show you that if you listen to my strategy, you made more money than randomly deciding to buy or sell. And it's the same idea here. I want to basically build models that shouldn't have a chance of winning. But maybe one or two of them got lucky. In fact, maybe 6 of them got lucky. So I built 1,000 models on the same data that I showed you. The red line that you see here, the true model that you see here, is where my actual default variable lies. I was able to get an area under the rock curve of around 0.58. Most of the data, 99.3% of all the other models were below that. But 6 models beat it. So my model was the 7th model. So again, how did we create this data? I randomly ordered the data. There shouldn't be patterns unless it happened due to sheer luck, unless it happened due to random chance. And that's what I'm showing you here. Is 6 times out of 1,000 it happened due to random chance. And then when John first showed this technique to me, I'm like, this is a p-value. Like this in its purest form is the definition of a p-value. What is a p-value? It's the likelihood that we see results that are as extreme or more extreme than the results we had underneath some null hypothesis. So assuming that there's no relationship, what are the chances of me seeing results that are as extreme or more extreme? This tells me that. What are the chances of me building this model, going through this technique, going through this procedure, and coming up with something that's actually better on the same data, just restructured and reordered out of the way? Well, really, there's only a 0.7% chance of this happening. So maybe you'll believe my model a little bit more than what you would have if I just told you it did a good job on a validation data set. Because again, now I'm telling you, I've tried beating my model. I've basically tried creating a control group to compare my model to, essentially trying to mask the placebo effect. Am I really seeing what I'm seeing? And it looks like in this model I am. If my true model was in the middle of this distribution, what I'd basically say is, look, I could reorder the data and come up with the same results. And that's probably not a good thing if I can randomly change my data around and still produce something that looks meaningful. So maybe it's a little hard to understand with this example, so I want to list a couple of other examples to maybe help you see it a little better. The first one is a student grade analogy. And I always like telling this example when I teach this to students is, let's imagine I gave you all a test and you studied really hard for this test. Well, what I'm going to do is I'm going to grade all of your tests. But then I'm just going to erase the name at the top of your test, and I'm just going to randomly put some student's name at the top of your test that's in the class. I'm just basically going to hand out results randomly to people. The students probably wouldn't be too happy about that. Or at least the students who studied a lot wouldn't be too happy about that. The students who didn't study at all might be going, oh, good. Whew, someone else can have my C. Fingers crossed, maybe I get an A. But that probably wouldn't be a good way of doing things. But that's the idea. Let's imagine I were to do that. let's see if there's truly a relationship between the number of hours that were studied and the grade that someone got on the exam. So let's imagine I only have 4 students in my class. They tell me that they studied, conveniently, 1, 2, 3, and 4 hours for the exam. And you can see what their grades are for each one of those hours studied here. Now, it looks like there's some kind of positive relationship. The R squared for this is 0.83. But then again, let's talk about the idea of target shuffling. How many different ways can 4 students get the grades 75, 85, 87, and 95? Well, with only 4 students, there are 24 possible permutations of these students' grades. And in fact, here are all 24 of those permutations. And so now, again, assuming that they studied for 1 hour, 2 hours, 3 hours, or 4 hours, here's all the different ways that those 4 grades could have happened if I were to find all the possible permutations. Well, there are 3 possible combinations that produce a regression with an R squared that's greater than or equal to our data. So again, only 3, well, actually, our data is 4. So 4 out of the possible 24 combinations are as extreme or more extreme in terms of results than the model that we had built on those 4 people. So can you see them? Here's all the permutations again. Let me show you ours. So this was the original data, where again, it looks like that the more hours you study, the better your grade is. Can you see the other ones? Here's one, where actually it's even better, where literally, every time you get more hours, your grade does improve. Can you see the others that might actually have a stronger relationship? Of course, it doesn't have to be a positive relationship, does it? It could easily be the exact opposite. Maybe every extra hour you study actually breaks your brain more. And so, you know what? Just study 1 hour, you did the best. Study 4 hours, you didn't do so well after all. So again, you can see there are 4 combinations. The other one is the same combination, the one right above the dark one that you see here. So again, 4 out of 24. There's a 1 in 6 chance that the 4 students I saw got the grades in the order of which they got them. Again, that's like a p-value. It's when I'm evaluating my model, it's like, oh, well, how likely is it that these results occurred? Well, the results occurred literally 1 out of 24 possible times. Or, I'm sorry, 1 out of 6 possible times, 4 out of 24 possible times. And that's all target shuffling is. It's permutation analysis. It's just, my goodness, with the data sets that we're dealing with these days, when we have millions upon millions of observations, I cannot get a computer to actually calculate all the permutations. So again, what I'm doing with target shuffling and what I'm doing with this random shuffling is I'm doing a simulation. I'm doing an approximation to all the permutations. I can't ask the computer to give me all the permutations when I have a sample of 1 million, but I can ask it to give me 10,000 permutations, and let's just see what I get out of that 10,000. So again, this is the beauty of computers, right? We're doing simulation here. So one more example to try and help drive the message home that we might be lucky. So I randomly generated 8 variables, all of them following a normal distribution, mean of 0, standard deviation of 8. And I specifically defined this relationship. Y is calculated as 5 plus 2 times x2 minus 3 times x8 plus some error. So I had to have some error in the model as well. Again, normally distributed errors. And then I performed target shuffling on the model. I performed target shuffling on this data, and I recorded a couple of things, again, to try and show people what are the results in terms of what we expect, and maybe some you don't expect. Well, with the 1,000 simulations that I ran, here are all the times that the variables x1 through x8 actually were significant. Now, these are the 1,000 simulated ones. So in other words, none of this is real data. None of this is. What this is the target shuffle data. And take a look at what you see. And you might be a little surprised. You're like, wait a minute, why am I seeing all of these variables appear significant? And why does it seem to be somewhere around 50 times that each of these variables appear significant? Oh, wait, look at the top. The p-value I used was 0.05. So again, if I were to do a statistical test and I'm allowing myself to be wrong 5% of the time, well, what's 5% of 1,000? Oh, 50. So of course I expect all of these variables to randomly occur 50 times in the 1,000 simulations that I ran. You know, variable x2 and x8 are in the real data, the real relationship, but when I'm randomly shuffling things, I could just get lucky and see any of these variables if I'm selecting them with that p-value. And you're thinking to yourself, well, you know, that's not so bad. 50 out of 1,000, I get a variable. You know, I'm not going to run into any obscure results that way, right? Well, let me show you another plot. Here's the number of times those variables occurred together. So for example, you can see that well over 600 times, in fact, almost 700 times, none of the variables were significant, which would make sense because again, this is all the randomly shuffled data. It shouldn't be. A little over 200 times, you see at least one variable was significant. But take a look. There were some times that 2 variables were significant. Sometimes 3 variables were significant. Sometimes even one time, 4 out of the 8 variables were significant. But we know that's not true. But we got lucky. And so again, the truth is that 2 variables are actually influencing y. But if I were to randomly shuffle my data, I could actually have a model that's quote unquote better. I found a model where 4 variables were significant off of completely randomly selected and randomly ordered data. So you can see again, hopefully with this, that sometimes we might get lucky. We need to try and show people how lucky we could be. And then it'll help people understand a little bit better maybe that our results are actually believable. It's like, look, I tried beating my model. I tried figuring out how lucky I got. And I didn't get so lucky. So it wasn't too bad. So in conclusion, validating models is not only important, but validating models is expected. We should always do this. We should always make sure what we're doing is right before we share our results with people, lest we run into the same problems and have an economist article written about us, where, well, you know what, we're just going to trust the results without validating it, and then those results don't end up being true. So to accurately explain how your model performs in deployment, validation is needed. One way of doing validation, and what I find to be a useful way of explaining to people validation, is the idea of target shuffling. The notion of me randomly trying to beat my model with the same data that I built my model off of, and trying to say, hey, look, you can give me your data. I randomly tried to make your data, you know, as good as it could be by reordering it as many times as I could, and I couldn't beat what I did, or I couldn't beat what I did very often. So you should trust the results that I got. I didn't just back into these results by luck or by happenstance. So again, what is the probability you got the model you did? Essentially, I'm trying to build placebo models or a control group to compare my model against. Sometimes we see the placebo effect. Sometimes the data goes, oh my goodness, there's things here that are not actually there. Most of the time, the placebo works as a placebo. Nothing happens. But we need to show people that we've actually done this. We've been doing this in clinical trials for years. Why not do it with every form of modeling that we could do? So a little bit shorter of a webinar than what I did last time, but again, I wanted to leave some room for questions. Thank you all so much for allowing me to be here, for allowing me to talk to you all today. Hopefully this has provided some insight for you all and some different ways of thinking about how to be able to handle our field. But I'd be more than happy to answer any questions you have.
Great, thank you so much, Aric. That was really, really interesting, and I hadn't seen it explained quite that way before myself. So we'll open it up for questions. If you do have a question and can type it into the chat box, then we'll be able to get those over to Aric. Aric, do you have the full reference for the Economist article?
Sure. Oh, I should. It's something I believe it was back in 2013. In fact, while we're gathering those, I can actually pull that for you. That is no problem.
That's fine. We'll probably post it possibly on the website if people want to look. And I couldn't quite read the graphic.
Oh, no, no, you're all good. That graphic is a small picture that I blew up, so you're safe. No worries there.
Great. So it does look like we're getting a couple questions in, so I believe you can see them as well, Aric. So I'll let you address.
Sure. Yep. And in fact, what I'll also do is I'll also put in the chat block for everyone to see. Here's the actual Economist article. It was written in October 2013, and so that's there for people. And then that's also there, Elizabeth, if you wanted to post that on the website.
Great. Thank you so much.
Sure thing. So first question that came in, do you have suggested methods of target shuffling for time series forecasting? I'll be honest with you. That is something that I'm a time series person. That's the moment I saw target shuffling, I was like, ooh, how can I do this in time series? And it's a little bit harder. What we do have in time series that I think is probably the closest approximation is what we call time series bootstrapping, where really, instead of taking one observation and randomly scattering it and randomly scattering our observations across time, we randomly scatter chunks of observations across time. So imagine, let's say you had daily data. So you take 2-week intervals and you randomly scatter those 2-week intervals across time so that the variables that are lags, let's say you built a model that was 3 lags back, those variables would still be the same. Most observations would still have their original lags, but the overall pattern of lag should be broken because it's not necessarily across the whole data set. So time series makes this a lot harder because we don't have independence. The beauty of doing target shuffling is in cross-sectional data independence. I can randomly shuffle things and it's okay. Time series is a lot harder to do. So that's something that I've been trying to figure out myself and arguing with myself many a times over. But that's probably the closest thing I can come up with to an idea for target shuffling in time series. So let's see here, another question. When you want to study the correlation between 2 variables, are you shuffling both variables or just one? So in that kind of scenario, again, we're just shuffling one variable. So if I were to do pairwise correlation, let's say between a target variable and an input variable, or even you can do it between 2 input variables, just leave one of them alone and just start randomly shuffling the other. Because again, all you really want to do is just randomly assign pattern. And so we do it a lot of times in model building because we want to say, well, the X's look the same. Our observations, our people look the same. We're just randomly shuffling the outcomes. When it comes to pairwise and individual, X versus Y and simple regression or in just pairwise correlations, you could probably get away with either one, but that's what we typically do is just shuffle one of them. So a follow-up to the time series one, do you shuffle the time series values at the time stamps? Yes, in a way. So it's basically take groups of time stamps and shuffle them. So it's sort of, take groups of them and move them around.
Great. Okay. Are there any other questions? It looks like a couple comments. Getting a lot of positive comments there. Thank you so much, Aric.
Oh, no problem.
Again, every time please go ahead, Aric.
I was going to say, and it's one of those things where, feel free to reach out to me individually as well. If you're afraid to ask a question in front of the group, I'm more than happy to respond via email. I don't actually have my email listed here. I have my website, but my email is my first name _ my last name @ncsu.edu. Just remember, Aric is spelled a little differently, so just be mindful of that. But yeah, feel free to shoot me an email as well if you have other follow-up questions.
Great. Thank you again, Aric. And thank you to everyone. Just to note that I did repost the topics of the upcoming NCASA remaining webinars for the year, the 2 machine learning. And I will point out here that the upcoming machine learning is a part 2 and part 1 is available on the YouTube channel, as is Aric's previous NCASA webinar on data science, which was titled, I believe, What Does Data Science Mean to an Executive? And that was a fascinating presentation. And then I've also reposted the links to the NCASA homepage and webinar page so that you can access that information. Registration is open for the machine learning part 2. So thank you again, Aric. We very much appreciate it. And well, we look forward to your continued involvement with NCASA, and hopefully we'll see you here again at a future webinar.
Definitely. Thank you again for inviting me. These have been an absolute blast to be able to do. I look forward to participating as much as possible.
Great. Okay. Thank you, everyone.